The problem we're working on at the University of Bath is energy storage. At the moment, only a few percent of electricity generated in the UK is from what we call renewables: wind, wave, solar, electricity. But there's a lot of incentive to have a greater proportion of our electricity supplied by these kinds of technologies, particularly to manage climate change. So we need some technology that can help us store the electricity, for example, during the day with solar, to deliver at night time when we get home from work. Well, in the Department of Chemical Engineering, which is my base at the University of Bath, we're looking at a number of technological solutions to this storage problem using hydrogen. Hydrogen is readily available. It's all around us in water. 11% of water is hydrogen. It's in biomass, you and me, and it's in fossil fuels. And there's a lot of hydrogen, and of course we see hydrogen every day in action. It's in the sun. That's what drives the sun. So we're not directly involved with the production of hydrogen, and we're not directly involved with the final use. We're interested in the middle bit, and that middle bit is how you contain the hydrogen. And just to give you an example of why it's difficult, let's imagine we're driving a car 300 miles. You need about 4 to 5 kilograms of hydrogen, which is about a third of the mass of gasoline that you need to go the same distance. So in other words, hydrogen produces a lot of energy per unit mass. The problem is it would occupy 60 cubic metres, which is 3 or 4 times the volume of your car. Now, no one is presuming that we're going to drive around with whopping great balloons behind our cars. So a problem is that we want to have the same amount of hydrogen but in a concentrated small space. And one of our biggest technical challenges is to be able to try and work out how to do this in the best possible way. At the moment, there are two main methodologies to store hydrogen in small, lightweight containers. One is by liquefying hydrogen. Now, liquid hydrogen, you have to go to temperatures that are only 30 degrees above absolute zero. Incredibly difficult to both achieve and maintain. The other way is by compressing hydrogen. That's at room temperature, but actually using pressures that may be 500 or 600 or 700 times atmospheric pressure, which have their own problems in terms of safety and management. So compressed gas and liquid hydrogen are the two main state-of-the-art technologies. We're looking completely differently. We're looking at using materials that got very small pores in them. Pores that may be only 2 or 3 molecular diameters across. That means maybe 2 or 3 nanometers in diameter. That's 1,000 millionth of a meter across. Now, it turns out that these pores have very special properties and able to contain hydrogen, and a lot of hydrogen. And we're trying to develop materials and understand how hydrogen behaves in these porous materials to be able to store them effectively.
My side of the research is focused on the materials and the experimental evaluation of their hydrogen storage capacities. Here at Bath, we take the most promising materials and we measure their hydrogen storage characteristics by passing hydrogen gas over them and measuring their uptake at different pressures and temperatures. Some examples of these materials are metal organic frameworks, zeolites, polymers of intrinsic microporosity, and activated carbons. And to give you an idea of how much hydrogen can be stored in these types of materials, so take for example this AX21 activated carbon. The amount of hydrogen that can be stored in that small amount of solid material equates roughly to the volume of this volumetric flask at standard temperatures and pressures. So these materials are quite good at being able to densify the hydrogen to make it easier to carry around. One of the biggest challenges is that it's very difficult to probe a gas inside of a solid material. So our most recent experiments have involved inelastic neutron scattering, which is a technique that is very good at providing information on the density and the state of hydrogen inside the pores of a solid material. Using this information, we can identify the most important design parameters. In other words, what makes these materials so good at absorbing hydrogen. And we can use this information to develop better hydrogen storage materials with higher capacities for the future.
As a fundamental engineering scientist, I'm absolutely on the edge of my seat with some of the results that we have in terms of what's happening inside these tiny pores in the materials that we believe, while I'm reluctant to use the word revolutionary, I think will cause a lot of excitement in the literature and in the scientific community. We've been the beneficiary of EPSRC funding for over 10 years now under its Supergen programme. Supergen means Sustainable Power Generation and Supply. These materials that we're looking at could be used to store hydrogen in motor vehicles, and they could be used to store electricity from renewable electricity, both of which have really positive advantages in terms of reducing carbon dioxide emissions, which then help reduce the impacts of climate change,